All right. Can you hear me, everybody, and those online? All right, thank you.
Yes, yes.
All right, perfect. Thank you. All right, so what we're gonna do today are a couple of things. First of all, I have here an example which I'm not gonna do as extensive as this is, but I would like you to read it. I will try to solve it for a more generic case, not just, so there are three, you remember I told you that there are three cases where you solve for a matched load. They're very important. We need to remember those, right? Rather by heart, all right? So and I'll tell you what we're gonna remember. The matched load, there are very important specific cases. What's happening when it's matched, when we have an open end at the end, when we have a short circuited line. I have a particular example for the matched line, but what I would like to do here is to solve it a little more generally, and then we plug at the end the match, which is Z naught, and then short and open. But you can see then the matched line solution as an example, all right? So I will add a page here. In fact, we will need a couple of pages, but I will call this one an example, and then you will have to read it as such. Okay, let me see. All right, so that is the line example. That is for you. After we solve the most general case, it's going to be very easy to do the example yourselves. All right. Yes, well, figure it out. There is a problem with this. Excuse me, I'm talking to a technician here for the problem. There's a problem with this, the power cannot come off.
Okay.
So I don't know whether it is this one. Has anybody else complained about this?
Mhm.
That there is a power on and off at times?
Okay.
So you may want to just keep it in mind. I don't want you to do anything at this point, you
Right.
know, it's
That's
just
fine.
going,
Yeah.
but there's time when it just comes off. I mean,
Okay.
stops, it goes
Okay.
off.
I'll come back after class.
Yeah, just look at the behind. I think there is something in there that is not,
Loose. Okay.
yeah,
I'll come back
it's
with-
kind of loose. Thank you. Yeah, I'm sorry, I had a problem here with the power, and that's why also it got a little bit of time to connect. All right, so let me move back, start describing the problem that we are going to solve. And I thought I was going to introduce the Smith chart, but since a lot of people are not here today, I understand that it is the ring day for the university and a lot of students are not in class. I will introduce the Smith chart on Monday. I want more people to be here so they can see more. And I suggest for those of you who are online, you may want to try to come to class on Monday, because the Smith chart is not an easy thing that you can see or you can learn on your own. And so it's a very easy thing to learn if you do the first few steps, all right? And after that is exactly the same kind of thing. But in any case, so today we're gonna solve the problem of a general line. So I'm gonna draw the line here. So we have a line. Always we show it as a thick line. And then let me also fill it up. So this is the one wire or one conductor, to be more accurate. This is the second one. This line, we give it, has a characteristic impedance of Z naught and a propagation constant of beta. Also, for the line, as you will see, we will always give either F or lambda. All right, if you have one, you know the other. And the relationship between these two is F times lambda equals C, where C is velocity of light, all right, in whatever medium is in between the two conductors. If I don't say anything particular, specific, then that is in air. So most of the time, what we're gonna see, it's gonna be for the ideal transmission line. This is an ideal transmission line, all right, now it's gonna be in air. But it depends, I will say here in medium, just in case you see, you don't forget that in the medium. All right, now what we do here is we connect at the end a load, and that's not how it goes practically, it's incorrect. We connect a load here. Usually the load, we will always show it like this. And then that's ZL. All right. And then on the front end, we will connect a source. But this time I will try to make the source more realistic, and I will put an internal impedance for the source. All right, so always, okay, let me see. Always I will try to do that, to have an internal impedance, because in most sources, there is an internal impedance. The source is not without an impedance. All right, so now what we said is let's do this here. So you remember that's the source. And this one. So this is VS. And usually I give VS here, and let's assume that is in volts. I will keep it now general, but in any problem, I will give you VS. And then the other thing you will have is the length of the line. And so usually what we do here is we go along the Z direction. These points, we name them A and A prime. This is the input port. B and B prime, this is the output port. So this, I want you, this is how you're gonna set up your problems with this kind of care. Not try to get sloppy, because in transmission lines, if you get sloppy with how you set up your problem, then you will always come out to make mistakes, all right? So here is the beginning. At the source, I will always put Z equals 0. And in this particular case, at the load, I will put Z equals L. And I will give you also L. All right, these are the things. And let me also move this one up here and make it smaller. So up here, you have everything that is given to you. And of course, ZS will be given and ZL. All right. So in this problem, I have given you, and if you wanna make sure that you don't miss that, this is given. This is given. This is given. This is the length. And these two are given in this problem. And you have to be very careful on how you set it up and how you know what is given to you. A lot of times, and I always stress it out, write down what you know, all right? And then what they're asking you to do. So in this case, I have not asked you yet what to do. So far, I'm giving you things, okay? Now, here is what I'm asking you to do. I want you to find the input impedance. So it says here, find input impedance at A prime. Do you remember how we have defined the input impedance? I will define it here for you so you remember it again. So input impedance, we normally show it like this at A prime. All right. The reason I'm saying that is because you can define input impedance anywhere on the line. So a lot of times when I write the input impedance, I will indicate it like this. And where? Because as you will see, the input impedance is a function of the length of the line, all right? And for that reason, I can find an input impedance at any point Z. We'll solve this and then I'll show you where the input impedance can vary. So now I want to know at what point I'm finding the input impedance. So I'm asking you to find this input impedance here, and for you to remember that this is what you need to find, I will, oops, no. I will give it this color, all right? So we are talking about this one here. This is what we need to find. Oops, excuse me. This one. Why do I do all of this? Because this is how you have to, at least visually, until you feel comfortable with putting down everything visually, you need to know, you need to see what you know and what you need to find. What is in yellow here is what you need to find. Everything else is known. All right, so that's how you visually classify it. Now, how am I going to do that? First of all, so the solution. Another comment, which I've made it many times, and those who hear me and do it have better chances of solving problems correctly. Rewrite your problem. A lot of times, people are trying to solve the problem without having read it carefully, and then many times they're solving a different question, all right, or missed questions. When you rewrite the problem, especially in transmission line problems, you better understand what you have and what you have to find. So in every problem, I will give you points for rewriting it carefully, all right? Otherwise, half of you are not going to solve the problem well because you're going to miss something in the process. So that's what I'm doing here. Solution. Input impedance. First of all, you have to remember how we define input impedance. The input impedance at any point on this line, let's assume point Z. This is point Z. At point Z, therefore, is when input impedance is a function of something, I write it like this, but when it is at a point, I always put slash and the point. All right, so now it's a function of something. That's why I'm writing like that. Is the ratio of the total voltage at Z divided by the total current at Z. Okay, that's the definition of an input impedance at point Z, which means because of that definition, then what do I have? As a result, therefore, of this, I have that ZL is the ratio of V at BB prime, total V, all right, of total V at BB prime divided by the total current and BB prime. When you don't see pluses and minuses in the currents and you see just V or I, that means total, all right? So voltage versus current at the end, where the load connects, which is the BB prime, is the ratio of these two gives you the load, all right? That's Ohm's law, from Ohm's law. And What else, therefore, do I have? For the same reason, my Z input at A prime, what is it going to be? V where? At A prime divided by what? I at A prime. Do you agree with that? This is just because of definition. Do you have any questions about this? Just make sure that you understand why I'm writing those two. Okay, I will call those 1 and 2. These are things that I know from the definition. Now I'm writing what I know, and you say here, known here. These are the known equations or known information. Okay, what else do we know? We know that the voltage, let me write it here, V of Z is equal. Now we have to write the equations. V naught plus E to the minus J beta Z plus V naught minus E to the J beta Z. Do you agree with that? Yes? No? Yes. I of Z. These are the equations I want you to remember. All right? When you see me writing things down, then you have to, without going back, I want you to remember those things. There are not too many, but it's going to be great if you remember them because you're not going to waste your time looking through the book. All right? And then you're going to remember them by practicing. So then, with I of Z, it's 1 over Z naught, as you will find in our above notes. All of this is in previous notes. But it's 1 over Z naught, V naught plus E to the minus J beta Z minus V naught minus E to the J beta Z. Where, these are all things we know, where Z naught, we know it is V naught plus over I naught plus, and that's how the I naught plus has been. We don't have an I naught plus, equals minus V naught minus over I naught minus. Okay, so these are all, if you go above, these are exactly above. You see, that's what we covered last time. So the above equations, I'm rewriting them. Okay, now I will define a new parameter, which I'm going to call the reflection coefficient. And now, so what is new definition, we have, let me add one more page. Okay, the new definition is reflection coefficient and the reflection coefficient, I show it with gamma, Greek letter gamma of Z, because it can be defined anywhere on the line. All right, a reflection coefficient can be defined anywhere on the line. I will come back to it because after I define it. The reflection coefficient is defined as the ratio at point Z of the reflected voltage over the incident voltage at any point Z. If you remember from also our previous things that we covered also. So here, this is the definition. And in fact, let me do something here. First of all, let's make it smaller to big. Okay, smaller to big. All right. So this is a new definition, and because it's new, I will do this so you can remember it. In fact, no, I will make it thicker. All right, so that's a new definition. Whatever I put in, these are important things to remember. These are the definitions, always very important to remember, obviously. Okay. Because of that, I will be able now to go and knowing what is B naught plus and B naught minus. So now I can say where B naught plus of Z is nothing else but this one. This is V, I did not say V naught plus, V plus of Z, all right? And therefore is V naught plus E to the minus J beta Z. That's also by definitions. And I, well, not really, let me not go to I first. V naught minus of Z equals to V naught minus E to the minus J beta Z. So practically, what you see is that, in fact, plus, where this is the V minus of Z. So now from 3, let me call this 3 then. Let me call this 4 and 5. From 4 and 5, first of all, and then 3, we have that gamma of Z. We put for V minus and V plus what we found here. Make them a little smaller, not bigger. Therefore, gamma of Z is going to be equal to V naught plus over V naught minus. And then we have E to the minus J to beta Z. So that means something very important, that if I know the ratio of V naught plus, in fact, V naught minus, I should say, you should correct me. Sorry, correct me. V naught minus, V naught minus, V naught plus. Okay, so if we know that ratio of V naught plus and V naught minus, practically I can find gamma of Z at any point on the line, all right? So that is an important relationship. And then also you need to remember that, or at least be able to derive it. If you don't remember it, if you need to remember, cannot remember all the time everything, but you need to remember 3, 4, and 5, all right? And then you find this relationship, which is 6. And that tells you that gamma of Z has the same magnitude everywhere on the line, but has a different phase. So what you observe from here is that gamma of Z has a magnitude, and that's the reflection coefficient, has the magnitude and a phase, and the phase is 2 beta Z, all right? And the magnitude of this reflection coefficient is constant, independent of Z. And therefore, the only thing that changes as a function of Z, and I will put it here as with a different color, is the phase. You need to remember that. That is important. You may not remember exactly the formula, so you can look at it, but you need to remember that the magnitude of gamma of z does not change along the line. That's extremely important property. Okay, if you don't remember them, write all of the important formulas on one page so you can find them easily. This one. Okay, important formula here. Now, why is this important? Because as I'm gonna try to find the input impedance at any point on the line, I will need to be able to know that one. And here is why. Do you remember now that I wrote this? All right, I'm writing here, I'm making a line, and now I'm working. After I put all of this theory down, now I'm trying to find the question that they asked me, to find the input impedance. So now I'm trying to find this. Okay, so now I'm gonna find Z in of Z. And I'm going to what I wrote. What is Z in of Z? Is this one here. All right, so Z in of Z, I remember it again from the definition that I wrote down, is gonna be V of Z divided by I of Z. But now I will do the following. I will go and rewrite all of my V of Z and I of Z in terms of the reflection coefficient. So I remember that V of Z is nothing else but V plus of Z plus V minus of Z. All right, remember that here? Total voltage is the total sum of the incident and the reflected. And I have defined, however, the reflection coefficient as the ratio here from 3. I have defined the reflection coefficient as the ratio of these two. So I can rewrite this one as V plus of Z times 1 plus gamma of Z. So practically, at any point of the line, if I know the reflection coefficient and the incident wave, then I know the total voltage. So that's another expression, all right? And as a matter of fact, I can rewrite this here as V naught plus E to the minus J beta Z, because that's your V of Z, plus and 1 plus gamma of Z. Okay, so either one you can do. I of Z, you remember is nothing else but 1 over Z naught, and then I have from here, this one here, let me use this one. This one here is V of Z plus, and this one here is V of Z minus. So practically, I can rewrite this as V plus of Z minus V minus of Z. That's your current. So now I can write this as V plus of Z divided by Z naught. And then what do I have in here? 1 minus gamma of Z. See what I do? This is very interesting. And as a matter of fact, for a moment, I will erase this because I don't need it. I need only the one above, even if you can use it like that if you want another way, but I will need these two for a moment. So I did not need this other expression. So I have these two. Now, if I take, let me call those 3, 4, 5, 6, 7, and 8. All right, from these two, let me make them a little smaller. There, so you have space here. Go back to Z in. I'm working on this. That's what I want to find. So Z in at Z is B of Z over I of Z. And I, from 7 and 8, what do I have? Now let me write it in blue. B plus of Z, 1 plus gamma of Z, V plus of Z divided by Z naught, 1 plus gamma of Z. Okay, so this one and this one cancel out. And what do we have? We have Z input at the point Z equals to Z naught, 1 plus gamma of Z, 1 minus gamma of Z. What does that tell you? That tells you that there is a very important property between the input impedance and the reflection coefficient. So practically, if I know the input impedance, the reflection coefficient at some point, then I know the input impedance, or reversely, if I know the input impedance, I know the reflection coefficient. Most of the time we know the reflection coefficient. So let me rewrite what we found now intermediately. Of course, you're not going to take this much time solving the problems. Now I'm teaching you also. We're developing the equations rather. So that's why it takes such a long problem. I will try to solve the problem for you to see how simplistically you can solve it. All right. So now we know that where gamma of Z, as we found before here in this expression, equals V naught plus over, minus, I should say, minus over V naught plus, and then E, to beta Z. Let me write it with an E. E to the J to beta Z. All right, we know that. Okay, so how am I going to use these two? Number one, let's see what happens. So practically, if I had known the theory that I gave you before, which is also a review, all of everything that I wrote before is theory, all right? So assuming that you know all of the above when I give you a problem, this is where you start with the solution, all right? All of the before, which we learned today, all of this from here down here is something that you will have available on when you solve problems, and you will know. You may want to recite them, you may want to have something to look at them, but you're not going to rewrite those definitions and you're not going to rewrite these derivations. All right, we'll do them once. So that's where the true solution of the problem starts. So now you come here and you say, okay, let me go and look at my line. I will bring the line down there to make it easier so we don't go up and down. So we'll make another copy of this. and move it down there. Copy. Paste. Okay. What happens at z equals 0? We have these two places on the transmission line where we have what we call boundary conditions. What are the two boundaries of the transmission line? The two boundaries of the transmission line are the beginning, where the line starts, where the source connects, and at the end. These are the two. And the beginning and the end, the two boundaries of the line, right? So we call whatever conditions we have here, which are usually circuit conditions. Circuit condition, here is the Ohm's law. The other circuit condition here will be a voltage divider. You will see what I mean, which we have seen. So at the ends of transmission line, you always have circuit conditions. We call them boundary conditions. So let me now write those conditions. I remember them because they are very familiar, but it's going to be easy to write them down. So the boundary conditions here are the following. First of all, at z equals 0. At z equals 0, we have the following circuit. And here, instead of the line, I will put z input at A prime. All right, and these are the 2 points where this applies. All right, how much is the voltage at A prime from this circuit? Mm-hmm. Yes, from voltage divider. Times Vs. Let's assume for, this is an important, this is voltage divider. Divider. So practically, if I knew Z input, I can find how much voltage applies at AA prime, all right? How much is Z input? We found from here, look at this. It's 8, let's call this 9. This one, Z input, is a function of gamma of Z, all right? And therefore, what we can write here is that V A prime equals Z naught, and then you have here 1 plus gamma at 0. All right, that's at AA prime. 1 minus gamma at 0, meaning Z equals 0. All right, because gamma is a function of Z. Okay. And then 1 over Zs, which is known, plus Z naught. And then you have 1 plus gamma of 0, 1 minus gamma at 0. Okay? And then if I divide both numerator and denominator by Z naught, that gives us, in fact, and then I divide both of numerator and denominator by this one. So then you get something simpler, which is 1 over ZS over Z naught, 1 minus gamma at 0, 1 plus gamma at 0, plus 1. Okay, so that's BAA prime. All right, all of these are derivative relationships, and you can have them available. I don't want you to rewrite them. I don't want you to rederive them. I want you to be comfortable knowing how we derive them, because I may ask you as a homework, for example, to do something similar, all right? To do a similar derivation, but not in the exam. In the exam, I'm not gonna ask you to rederive things. Okay, so we have that. Therefore, if we find gamma at 0, we know VAA prime. You agree? That we keep it in mind. That's 10. Let's go to the other boundary conditions. So this is the front boundary condition. Let's go to the load now. What do we know from the load? We know that ZL equals with V BB prime divided by I BB prime. Therefore, what do we know from Z input? Z input at BB prime, because Z input is defined the same way, all right? V of Z at I of Z. Z input at BB prime equals to ZL. That's your boundary condition. Okay, let me see. Do it better. So now, how much is Z input at BB prime from 9? Z input at BB prime, therefore at BB prime, which is equal to ZL, is gonna be equal to Z naught 1 plus, make sure, gamma Z 1 minus gamma of Z. Okay, and that is equal to ZL. Therefore, from here, what do I find? Let me rewrite it a little easier, and you will, and then of course this is Z equals L. Let me write it here. Sorry. Z equals L. Z equals L. All right, or Z naught. Another way of when we write the reflection coefficient at the load is like this, where sometimes you will see it very often. Gamma L is gamma when Z is at the load, when we are at the load, all right? Or you can see it at times either as gamma L, or you can see it as gamma BB prime, the same thing, all right? People, depends on where you are, whose notes you read. Most of the time, people will write it like this, but there are many times we write it like that. It's the same thing. Why do we write it like gamma capital L? Because it means at the load, all right? But if the load is complex, or if there are other lines, we write it like this, which means that it's gamma at BB prime. And so a lot of times people will indicate it like that. If this is my reflection coefficient, they will call this at BB prime, gamma at BB prime, or gamma at L. And they will call this gamma at AA prime, all right, or gamma at 0, which is gamma at 0 here. And in fact, I instead of writing like this, I'd rather write it as gamma AA prime, to tell you the truth. I have flexibility as long as you remember what it is, and then you know that it's the same thing. all right? There. So you remember gamma A prime, and the other is gamma B prime. So from this equation here, all right, I can rewrite it, and I can find gamma L from this equation. So gamma L here, it's a very important equation where I'm gonna write it because it applies to every time you have a load there with one impedance. Gamma L, you will find out is gonna be ZL minus Z naught divided by ZL plus Z naught. This is a very important equation. All right, very important to remember it by heart. That every time you are at the load, this is the reflection coefficient at the load, and it came down from these previous equations. All right. So now I know the reflection coefficient at BB prime. Okay, let me see what I found for gamma of Z. You remember this one here? Equation 6. Let me take equation 6. From, therefore, equation 6, what do I find out? That gamma of Z is nothing else but V0 minus over V0 plus. And then I'm going to ask V0 minus over V0 plus E to the J to beta Z. What is this one here? Do you know? Is the reflection coefficient where? At the source. It's the reflection coefficient in the beginning of the line. A prime, you see that? Is the reflection coefficient here because when Z goes to 0, gamma at 0 from here, gamma at 0, which is right there, it equals this one. This goes to 0. So this one is nothing else but the reflection coefficient in front in the beginning of the line. So gamma A prime, then we're almost done, or we're late. Okay, so I will write this down, that this one is gamma A prime. And we will continue from there because now we are very close to finding these expressions. What I would like you to do for Monday, please read this. All right, all of this, because it primarily has everything that we have done. But if nothing else, from this point on, from here down, for Monday, I would like you to do that as an exercise. Monday, from here all the way down, read this. And I will give you also a quiz. So remember that it's going to be a quiz. I will activate it right now, but after you leave, because there is another class. But read this, be familiar, because that is the foundation for everything we will do. All right, and it's going to be always the same. These 3 or 4 pages is the foundation, nothing else. All right, and then we'll continue from there. Any questions?